Hello everyone, I am Zhangji Jia, a student of Universidad Autónoma de San Luis Potosi. Today I would like to introduce the funcontainerization and application of clay to you, hoping to help you better understand and apply clay materials. The first is clay and its funcontainerization. Clay is defined as a stratified silicate mineral with a particle size of less than 10 m, which can be divided into B11TO type and 21TO type, because clay has a large specific surface area and rich surface functional groups. It can remove cationic pollutants through electrostatic attraction, surface complexation and ion exchange, so it is widely used in the removal of pollutants. However, natural clay is often rich in impurities, and the active site is not excited and it needs to be modified and functionalized to be better applied. Heat treatment clay is dehydrated and dehydrogenated by heat, which changes the composition and structure of the clay. At the right temperature, heat treatment can improve the specific surface area and porosity of clay, change the surface charge, and thus improve its adsorption performance. The method of acid treatment of clay is through strong acid treatment so that the interlayer exchangeable cations are replaced by hydrogen, while the octahedral ions Al, Fe, Md ions are lost through leaching and acid enhancement. Acid treatment can increase the specific surface area of clay and the number of adsorption sites. It is a common means of funcontainerization. Next is the inorganic columnar modified clay. The method is to first embed the clay with the columnar agent, and then calcine to obtain an irreversible oxidation column to support the clay layer, thereby enhancing its adsorption capacity. The clay modified by inorganic column has permanent pore and interlayer structure, and its specific surface area and pore size are effectively increased. Clay stripping is an emerging method of clay funcontainerization, a process that uses ultrasonic treatment or shear as a driving force to separate natural clay from its blocky fermented nanostructures. The stripped clay is imbued with the structural properties of a low-vis amine material, which not only greatly increases the specific surface area, but also completely exposes the active adsorption site on the clay surface for reaction. Another direction of functionalized clay is organic modification, including polymer modification and organosilane modification. The polymer modification step is to add polymer into the interlayer space of clay minerals by physical adsorption, chemical grafting or ion exchange, which can improve the adsorption performance of clay minerals. Due to the abundant hydroxyl OH, carboxyl COOH and ENH to groups on the polymer molecular chain, polymer modified clays can form specific interactions with pollutants, resulting in strong and even selective adsorption. Organosilane modification is another method of organofunctional clay. The principle is that the alkylsky group of organosilane is hydrolyzed to form a silane OL group, which reacts with the aluminum hydroxyl group on the clay surface to form a covalent bond, thereby grafting the organic functional group to the clay surface. The grafted organic functional groups, such as amino unsulfidable functional groups, can selectively adsorb specific heavy metals and organic pollutants, which is a relatively advanced functional method at present. Next, we take a specific example, the properties of organosilane modified clays and their adsorption of dyes. The specific synthesis steps are as follows. First, in the grafting reaction, 3,2-aminethyl amino propyl trimethoxysilane E, an alkaline medium with a pH of 1012, releasing methanol in the 3,2-aminethyl aminopropylsilane SPEDA group, which reacts with the hydroxyl group on the clay surface to graft onto the clay. The properties of the functionalized clay have undergone great changes. The first is the change of layer spacing. After grafting with SPEDA group, the diffraction pattern of the modified clay has a reflection change in the low-angle region, and the interlayer spacing D1 is between 153 and 230 nm. The spacing between layers is increased by more than 150 times, and the expansion rate is increased by 50.33. Next is the change of pore structure and specific surface area, which are reduced due to the entry of organosyl groups into the clay pores. At the same time, the clay surface potential changed significantly after funcontainerization. The PHP's ETH values for MMT and PSPEDA blends are 6, 77 and 9, 83, respectively. This shows that after SPEDA molecule grafting, a large amount of nitrogen is introduced to make the clay surface change from neutral to alkaline. In addition, the thermal properties of clay also change. By thermogravimetric analysis, it was found that after grafting SpEDA groups on the surface interlayer space of montramethylase, the material obtained higher thermal stability due to less moisture in the silicized rupturing clay structure. Finally, the change of functional groups on the clay surface is discussed. FTIR analysis shows that organosilane modified clay TSPEI exhibits to new infrared characteristic peaks. 1546 cm 1 weak, and aged to bending in 1448 cm 1 wide. CH of bending, indicating the addition of new functional groups to the surface of the modified clay mineral. Finally, the modified clay was used for the removal of dye waste. It was found that the modified clay had excellent adsorption properties, and the adsorption capacity reached 171 for 318.6 mg1. In addition, the adsorption energy of unintercalated montramethylase for dye molecules was 34 2 kJ, while that of intercalated montramethylase for dye molecules was 23 6 kJ, indicating that the modified surface properties and adsorption sites had changed. That's all. Thank you for watching.